What? What? Oh, we have some. Oh, we have some music today. What am I doing? I don't even know what I'm doing. Caleb's here. Invite him. Turn the music off. Perfect. Sorry, I'm running a little behind today because of I don't even know where I put the book. Actually, let me change my screen real quick. Let me turn off that for a sec. Let me know if you if oh let me know if you could hear me or not, Caleb, because I know Discord gave me like some crap the other day. Okay, let me turn this back on. Oh, I gotta turn my VM on too. Sorry. All right, I'll turn my screen back on. What up? Well, we got chat. Hello, everyone. Hope you're well. I'm a little unprepared because my boy just called me and was just venting to me a little bit about some stuff. So my bad, my bad. You know, people come first, man. You know, I've got to help people that are in need help. What do I want to do here? Yeah, I want to do this. Cool, Project Scratch. What we're doing. Yeah. Dope. All right, we're in. Cool. All right, I'm gonna get started. Clearly, I can't type. So, welcome, everybody. I have the comment stuff here, just in case. We are on the last meeting of writing an interpreter in Go. This book is actually, it was really fun. I mean, I don't know where I put the physical copy. I think I put it back there. This book was really fun. And I liked this chapter a lot. So we did chapter 4 this week, which is extending the interpreter. We built up pretty much everything that we needed to build up, and we have like lexing working, right? So we can take source code, make it into tokens. We have parsing working, so we can make those tokens and put them into an abstract syntax tree. We have evaluation working, so we can walk the abstract syntax tree and actually like evaluate values and logic. But we didn't have certain data types for a while, right? So if I actually open up my terminal and I do go run this, we didn't have certain data types for a while. We were only able to do like let x equals 2, right? And do this and then do x. But now in this last chapter of the book, we started doing things like this. Let x equal foo and x. Now we have strings. Let x equal, I don't know, an array. 1, 2, 3, and x. And we have hash maps. Let x equal oh, sorry, I missed the enter there. Let x equal, and then like, foo bar. Awesome. Boom. So we didn't have these last week. We only had like basic integers to assign to our variables and integers and booleans. So this latest chapter is chapter 4, and I'm going to go back to the book, and it's called Extending the Interpreter. So what are we doing here? In this chapter, we just built a bunch more new data types, strings, arrays, and hash maps, and we added what are called built-in functions. So like, I don't know how familiar the audience is going to be with programming in general, but generally speaking, a built-in function is let me make sure my audio is not off because I thought I had muted myself before, but I didn't. Great. A built-in function is a function that's literally built in to the interpreter that you're using. Now, you might think of this as like a standard library, but it's not exactly a standard library because it's actually like not a separate package or separate feature. It's built into the interpreter itself. If you are familiar with shell scripting or like Linux, you might, let me get out of this for a sec. You might know that they like your shell has certain built-ins inside of it. So if I was running the bash shell, I would know that like type ls or type cd, these are a shell built-in. So like you'll see here, this is actually pretty cool. I want to show you this for a second. What's a command type Terraform? Great. So I have a command in my shell called Terraform, but it is really like a command that was added, right? I downloaded Terraform and I put this in here. But if I did type cd, it says cd is a shell built-in. So this is the same concept that we're talking about in this interpreter book, is that your interpreter is not only responsible for like parsing commands that it gets passed to it, but some commands could even just be built into the interpreter that the user does not have to define, and the user doesn't have to like write any logic for it. It's just there for them to use it all the time. And that's similar to like a shell, because a shell, like a Linux shell, like bash or whatever, they are a type of interpreter, right? Because they interpret commands. When I do like echo, hello, my shell interpreted this as a command and printed out the result. No different than the interpreter that we're building in this interpreter book. So I just want to show you the built-ins there. Cool. Going back to the book for a sec. So the author says our programming language looks pretty cool right now, but it's missing a bunch of stuff, right? So let's add it.
Hello.
Yo, what's up, Caleb? How's life? Can you hear me? I don't know if you can hear me. I hope you can hear me. Let me see. Can you hear me, Caleb? Discord does this weird thing where it's like, doesn't want to use audio device. Let me just double check real quick. Hold on, I'm gonna disconnect real quick. Disconnect quietly, go there, listen in, speak on stage, pop out. Can you hear me now? I think it's because it like takes my mic away. Let me get you the stream real quick. I got to figure out the audio routing for when I'm streaming and want to speak in Discord, because it is not great sometimes. I think it's because I start one app or the other.
I think I could hear you.
Can you hear me on here or on YouTube?
Yeah, I can hear you on both. Do you prefer YouTube or?
I don't care. As long as you can hear me. I think it's because I started the apps out of order.
Okay.
And like Discord was trying to control the mic. But if you can hear me on both, we're good. Cool. Yeah, sorry. Welcome, by the way. Yeah, so this chapter was about extending the interpreter. We built up a lot of like the logic here so far, but we don't have any like string data types, array data types, or hash data types. So like this chapter was all about adding those 3 data types and about adding some built-in functions to make our lives a little bit easier, like the length function. I don't know if you finished reading for this. Did you have any questions you want to cover first?
Mm-mm.
Okay, cool. I'm just gonna like linearly walk through it and do that. So the first up, the author covered strings and basically said, strings are as we know they are. Like strings are as we already know them to be if we're familiar with programming languages like other programming languages, just a string of characters, right? But strings can also have like operations that can be done on them, like concatenation, right? You should be able to concatenate strings together to form like a larger string. And we do this very, very frequently in programming. So this is the first like thing that we're going to do is we need to support strings. And like looking at the code, I think I'm just going to open up the code directly. Parser string. Yeah. So what we needed to do first off is we needed to make like a new token type that tells our like Lexer, hey, you can actually read strings now and build tokens for them. So let's go with Lexer real quick. String. I want to see where he put it there. I believe it was in here. And all we did to our Lexer was add a new character that we can parse. And strings in the Monkey programming language are going to be with double quotes. So if we're doing a lex over the source code and we encounter a double quote, we now need to like parse that as a string. And this is actually one of the simplest like lexing like operations that we can do. And I thought this was pretty nice and straightforward. It kind of brought us back to chapter 1 for a brief moment of doing lexing. But if we're iterating over the characters in the source code and we get a double quote, we know that we are starting a string. So we mark that token type. And then we read the string. And read string is not as fancy as you might think. You literally just walk the characters until you find another double quote or you find the end of file. And then you just save that as a string token. Ta-da.
I thought that was like such a simple and elegant
That's
solution.
what
I was
I
expecting
thought.
it. I thought it was going to be so much more difficult to like,
Me too.
iterate through and figure out when to not tokenize it all together. I thought that was really,
Yeah.
really cool.
Now I don't think this works for like let x equal like a string like this, like Matthew / quote. I don't think this works because it's it does work. Well, no, it doesn't because it missed this. Yeah. So I guess like there needs to be some special cases added to the like program to make it like parse escaped strings and whatnot. But for the most part, for a simple string lexer, I thought it was fine. I thought that like worked pretty well. I honestly expected it to be more logic here, so I was pretty surprised. So yeah, so once we had the string lexing, we actually did parsing, and you can see here that we registered a new prefix operation for strings. Why prefix and not infix? Because strings are always going to be started with a double quote, right? So there's only going to be one operand on the right side of it. So we do a prefix operation here saying, hey, if the token we got was a string, we'll then parse the string's literal. And parsing the string literal is quite simple. You're just pulling the token's value out and storing it as your AST node. So this is like all the changes we had to make for this, which I thought was cool. And then the last one was, I think this was an object. I don't remember where this was. Maybe it's an evaluator. I didn't look at the full source code beforehand because I got a phone call. Yeah. So the last like object that we needed to do to add string support was just update our evaluator to take that AST node of a string and return an object. And ta-da, we have strings. That's literally all we needed to do. At least what I remember from the reading. That's all we need to do is just update the lexer with these like little lines, update the parser with these, with the type. Yeah, with the type. And then update the evaluator to actually evaluate the strings. So really small code changes for a big improvement on the language. Now we have strings. That was pretty much it for strings. But then the author said, great, we want to be able to do more things with strings, like concatenate them. So he wrote tests to make sure that like, hello plus world would give you like hello world as one string, but hello minus world would not like allow you to do that because you can't like subtract strings. And the only thing that the author had to do here that he was saying, I think it was it in evaluator.go? Let me just make sure. Yeah, was this. It was string. Oh yeah, this. Right. All they had to do was add this line and it just magically worked. Now you have string concatenation. So I thought that was interesting where we're reusing the same like infix expression stuff that we've been using this whole time. And the other cases up here are for like integer addition, equality, right? We already covered those in a previous video, but we added this new case here saying, hey, if the type that we've got is a string and there's a string on both sides of the operator, let's actually add those strings together. Let's support that operation. And if you go into this function, all it is typical. The magic here is, I'll show you in a second. If the operator passed to this function was not a plus sign, that's an error, right? Because we're not supporting like string subtraction, whatever that might be. We're only supporting string concatenation using the plus operator. So if we reach this point and we don't have a plus operator, that would be a evaluation error. We should print that out to the user and get out of here. Then we just get the left and right parts of the string and we make sure that we do a type assertion here to make sure that they are of type string, because we don't want to be adding things together that are not strings. And I wish the author wouldn't have done this, but the real magic here happens right there. So we're taking the two strings that we got from our parser, we're getting the both strings, and then we are using the underlying Go type system to concatenate strings here together. That's literally it. I wish he wouldn't have reused this plus here though. I kind of wish I would have seen something like this. Value format dot sprintf sprintf. Yeah, this. I wish I would have seen this %s left val. Oh, my key bindings are not updated on this computer, on the system. Right val. There you go. I wish I'd have seen this personally, because it would have made the magic more explicit. I know this is another function call, but it's really easy to miss this plus operation here and understand that this is not the monkey's plus operation. This is the underlying Go's plus operation. So I don't know. I just wish they would have made that magic kind of a little bit more explicit. So yeah. Any questions on strings?
Nope.
Cool. Let's move to built-ins. So I thought this section was interesting, and partially because, I don't know, when I was reading it, part of me expected something different. I expected something like more difficult than what the author came up with, and I'll look at the chat just to make sure. Hello, Max. Part of me expected something different here, but built-ins are pretty interesting, and I'll go to the thing, object.go, object, I can't type. There we go. So a built-in function gets its own type in our monkey programming language, right? And the type is kind of like a more generic type if we look at it. Not like generics for Go generics, but just generic in the term, in like a light way of using the term. It's any function that takes 0 or more objects and returns one object. If that is your type, then you are of type built-in function. And I thought that was really interesting because, like the author said in the book, this allows us to call any built-in functions with like an arbitrary number of arguments, and it still works. So I thought that was pretty interesting. And we added a new object for that built-in function to like support our AST, like being able to read it. And the author gave us the length function. So I want to show you that. And I think he put that in evaluator. Yeah, evaluator built-ins, great. So I want to show you that, built-ins. So ignore everything else for this very second. And also ignore my linter telling me that you don't need this. It's fine. Great, there you go, it's gone. Oh, I thought I was gonna do it for everywhere. It's fine. So this is all we need to do to implement a built-in. We had to create this new map called built-ins, which I'll show you where it's used in a second. It's right over here. So we created this new map called built-ins to hold our environment state, and I'm doing quotes here on the camera, to hold our environment state to hold built-ins so that we can use it. So I think it was last week. Yeah, I think it was last week that we created this concept called an environment, so that if you created like variables or functions that were like nested, you would shadow the environment from your parent. Here, we're creating a new environment called built-in that kind of shadows, or that is global across our whole program. So if we don't find something in like if we don't find like a shadowed version of len, right? Like let's say we called len. If we don't find a shadowed version of len in this environment, then fall back to the built-in and use the built-in. So I thought that was cool, but it's also an odd behavior in my opinion, because this allows you as a programmer to override built-ins, which may or may not be something that I think this language should allow, but it looks like the author is allowing it. And I'll show you that in a sec. But yeah, all we had to do was make that map, add it to our environment, and now we have the ability to call built-in functions. And the built-in function that the author created here was called length. And here's that function signature that we just saw before, right? A function that takes 0 or more objects and returns 1 object. And this is it. This is how you do length in this monkey programming language. You check that you have at least, exactly 1 argument. Otherwise, that's an error. And then you check what type of argument you got, and you return the length of its value. Ta-da! Now we can do this. Go run this. Len, Matthew. Boom. And that works. But it doesn't just work for a string. Oh God, I forget that this makes you type every character one at a time. It works for arrays as well, because we have that built-in switching on the type that's passed to it. So I thought this was pretty neat. Any questions on like built-in stuff? Let me see if there's anything I missed with the book. Yeah, we covered the environment. Yeah, and we covered the switch. Cool. Any questions there from anyone? Sweet. And then from here, it's just rinse and repeat until we get to the end. Now that we have strings working and like our first built-in added to the language, we can start adding other types. And these are a little bit more complex types like arrays and hash maps. And under the hood, the array is going to be using a Go slice. So a Go slice is like a dynamic list or dynamic array in Go. It's going to be using that under the hood, which is nice. And we'll be able to do like indexing on the array to get like the 0th element or whatever. So that's kind of nice. What I thought was interesting here was this, and I'm trying to find it real quick. Not this. We add the tokens, like that's fine. We know how to parse tokens. But I thought, let's see. There's a place where he makes it use a infix operator, and he kind of calls it out in here, and I'm just trying to find it real quick. Yeah, I don't know if I can find it real quick. Yeah, right here. Okay, so I'll cover the array first, and then I'll cover the part that I thought was actually pretty interesting. One, to support arrays, again, we need to lex the tokens. Then we need to parse the tokens, and parsing tokens is pretty straightforward. You kind of just iterate again and again and again, which is what he's doing here. If you have a left bracket, you build your expression, and then you like go to the end essentially, and by like iterating through each token. And since these are comma separated things, we basically just for every comma we get, we build a new expression out of it. So this was like nothing complicated here that we haven't already seen before. We've actually seen more complex parsing logic when we did like nested functions. This is just walking a list, and every comma, it's going to like parse an expression. So it's like left bracket, get to the comma, parse expression, get to the comma, parse expression, get to the comma, parse expression, get to the right bracket. Okay, we're done. That's all this is doing. Cool. But that I didn't find too interesting. That was fine. What I did find interesting was how the author thought about indexing an array. Like we all know how to do this if we're into programming. You do like let x equal like an array of 1, 2, 3, or that's probably bad. Foo, bar, baz. So now we have an array. If I print it out, I get the whole array. If I get the first element, I get foo. And if I get the second index, that's the last element, I get baz. Like we know how to use arrays, and this is cool. But this index operation here, I thought the way the author treated this was interesting. He said that, where is it? We're not going to be using the prefix operation for this. We are going to, and I'm trying to see where he says this. Yeah, right here. Okay. We're not going to be using the prefix like operation here. So when we encounter like the left bracket, we do like a prefix parse. He says we're not going to do that. We're actually going to do infix parsing, because we're going to treat the left bracket as like separating two operands, being this. Let me write it in code. Actually, this is fine. We're going to treat and I'm going to probably zoom in for a sec. Oh, can I not zoom in this? It's fine. Yeah, I can't do it. No, there we go. Okay. We're going to do something like this, where x0, the author says, if I encountered this left bracket here, I'm not going to parse it as a prefix operator, because that would actually miss what I need to do. Instead, I'm going to parse it as an infix operator, right? Infix being like in between two other operands. And I'm going to call the array itself the left operand and the index inside the right operand. And I thought that was very, very interesting, because you do need both. You can't index an array without the array, right? You need both the index and the array. So making this an infix operation means that you do have both access to both sides. So I thought that was a really, really neat trick. And honestly, when I was reading this section, I was like, oh yeah, we're just going to do a prefix operation here. It's going to work. And I was totally wrong, right? I was wrong. So that was cool. Any questions around that? Because I know that like probably doesn't sound as clear at first. No, Matt, everything sounds great. You're great.
I agree with that.
I heard a little laugh. It was good. Thank you. Cool. And then the author says, once we like thought about that and noticed how to do it with the infix operator, we just register the infix parsing function for the token that you want to be the infix. And here it is. And then the actual implementation of the function is very simple. You get the left side, and then you parse the next like side of it, the index side, and then you return the expression. So pretty simple. You get the left and the right. But the author even notes that this doesn't fix the test cases, because we're not parsing at the right priority here. Like we're parsing the expression like lowest, but it has no idea how to treat like these right brackets, whether they should be like higher precedence or lower precedence. So the author says the only way to do that is to get a highest, like put the left bracket as the highest priority, right? Basically saying this should be parsed first, and then that makes the test pass. Cool. What else? So now at this point we have a array that is parsed correctly, and now we need to actually evaluate it and print out its objects. One design choice that the author made here is that the arrays can hold arbitrary types. So normally arrays in Go, or lists or slices in Go, can only hold elements of the same type. The author makes a point here to say that these arrays can hold like any types. So I can do this, let x equal 1, foo, and like true or something. And this will work correctly. They don't have to be the same type in this monkey programming language. So keep that in mind, because it matters. When we say like what an array is, you'll notice that an array is a slice of objects, where an object can have like a type for it. So just keep that in mind. This makes the array like have any type we want. So cool. I don't think there's anything else to discuss here based on like what I read. Yeah, I think we're good here. That was pretty much it. Awesome. Any questions so far before we cover the last part of the index operator? Sweet. Just like interrupt me if there's questions. The last part of making sure arrays are fully functional is making sure that we're actually taking the index operation that we're getting and really getting a value back, right? Like going to actually evaluate it and get the value under the hood. And I'm going to kind of skip the test cases because they're pretty boring. The only thing you need to know here is that when you do encounter like in the actual index expression, right? If we do encounter like an index expression, meaning we have an array that we're trying to index, we have to do a few things here. We have to get the left side of the expression. We have to get the right side of the expression, and then we have to evaluate it. Makes sense. And under the hood, when you take a left and a right and you evaluate it, you have to then do some assertions to make sure that both sides that you're getting like are of the correct type that you need. So what does that mean? That means the left side needs to be an array, because you can't index anything other than an array. That would be a syntax error. And then the right side needs to be an integer, because you can't index an array with like a string, right? I couldn't do like x of like foo or something, or like x of, index foo. I couldn't do this. This gets me a error. But I can do, god damn it, I can't like go up and down with this. I can do integers here and I get the values. So that's going to matter when we talk about hash maps. And that's arrays. I don't think this part's super important, honestly. Like evaluate array index expression. All we're really doing here is taking the array, making sure that it's the correct type, and then making sure index is the correct type, and then just literally like returning the element at that index with some like bounds checking. So nothing crazy here. Cool. And now we have arrays. And since we have arrays, we can update some of our built-in functions to account for arrays as well. Because before it was only working on strings. And then the author takes it like 3 steps forward and says, we're going to add more built-in functions to arrays. We're going to add a first function that takes an array and gives me the first element. We're going to add a last function that takes an array and gives me the last element. And then we're going to add a rest function that takes an array and gives me everything but the first element. So he was just basically kind of, I'm not going to say flexing, because he wasn't really flexing here. It was just, he was basically just saying, hey, look at the cool things we can do with the language now when we have more types to work with. So I thought this was pretty cool. And I can show you that on the command line. You can do first of x and you'll get the first element. You can do last of x and you get the last element. And you can do rest of x and you'll get all the elements except for the first one. So pretty cool. Okay, and then the second to last subchapter in here, right? Yeah, is hash maps. This was another one where I thought was going to be a little complex, and it ended up being simpler than I thought it was going to be. And there was a part in here that made me double take and reread the section for a second, and I'll show you what that is. Hash maps. So hash maps are interesting because hash maps, we know like what they are, right? Like we know that they're a map of keys to values, and the keys have to all be unique. But the author said, hey, I don't want just string keys because that'll limit like my map. I want to be able to have like other keys, like integers or anything that's kind of comparable, essentially is what he was saying. So he said our hash map under the hood, like the Go type that it's going to use under the hood, can't just be a map like string or like a map object. We can't do that. That's what he says here. And I'll get to that in a second because I know he covers lexing first. So we'll just rewind real quick to lexing. The author says for hash maps, the only real new thing we need to do here is lex based on our tokens. And the author says the only new token that's in this input is going to be the colon, right? Because that's the only one that we have not actually lexed first. We've lexed the left and right braces with like functions and conditionals. We've lexed the double quotes for strings. We've lexed everything else for like identifiers and everything else, but we never lexed this colon yet. So we need to add that to our lexer if we want to actually lex hash maps. Okay, sorry, I know that was like a lot of vocabulary. But what does that mean? We need a token for it. So we need to know the colon is a colon token. He wrote a test for it. And we need to update our lexer to just say, hey, anytime you run into a colon, please give me a colon token. Congrats, you're done. Moving into parsing, we have to parse these hash maps in this kind of format. It will be a left brace, left squarely brace, whatever you want to call it, an expression, a colon, an expression, a comma, and repeat that over again. So it's comma separated lists of expression, colon, expression pairs. What does that mean for code? That means for code, we need another type to store these expression pairs. We need a literal, and we need like its methods. So we're getting to the point where I was like a little confused for a moment, and we'll get there in a second. Once we have the type, we can now update our tests and update our parser to say, hey, here's how I'm going down to the actual code. Here's how you parse a hash map. You register a prefix expression for it, because anytime you see a left brace, I want you to parse a hash map if possible. When you parse a hash map, you need to build the literal value and parse all of its pairs. And you just walk down the actual hash map and you say, hey, if I got the key and if there's no colon in between my key and value, that's a problem, return nil. Otherwise, there's a value, get it out, add it to the pairs that we've seen so far. And if the hash map doesn't end with a right brace, that's a syntax error, return nil. So like you just keep walking the hash map until you get all of your key value expressions and you store them in pairs. So I thought that was pretty interesting. And then you return that back. And that gives you what you need to now evaluate hash maps. So we'll move into that. But before we did that, the author makes a note here, and this is where he starts talking about the part that I was slightly confused about. Yeah, right? This is where he says this. Yeah, okay. So the author says we can't just have this. We can't just make our actual hash type, like the underlying type in Go. We can't make it just a map of object to object. Because if we did that, then we can have a case where we store like a string key with a string value, but then like a bool key with like a string value, and Go like won't be able to tell the difference between the string and the bool, whether or not they are like the same hash or not. So basically what the author's saying here, he gives an example, I think down here. Yeah. He says, if you did this and you made like one key pair and you put it in, and you made another key pair and you tried to put it in, you would get like a collision essentially. So yeah. And you wouldn't know how to like actually determine whether or not one, like if I meant one key or a different key. I don't know if I explained that well. Let me try it again. Trying to explain this in a way that makes like perfect sense clearly. I think he has a better test case down here. I thought he did. Or up here. I know it was in the book. 1 second. Yeah, right here. Yeah. I think this test case explained it better than the test case down here personally. If you had a hash map and the key is name and the value is monkey, right? And you accessed a literal key name, how do you know that this name and this name are the same? Like you would never know, right? Even though they're the same string, when you've like parsed this will be a string literal and this will be like an expression essentially, right? So how the hell do we know that these two like keys are the same? And that's what the author was demonstrating down here, is if you created like two strings, put them in the maps, you'll have no idea whether or not these strings were the same, even if they contained the same value, right? So like name1 and name2 both contain the string name, but when you do a comparison on them, they're not equal to each other. So you'll never know, like you'll never be able to use them to key off your map. And the author says like, that would suck for us. And the solution that the author came up with was to create a new type called like the hash key. And this hash key allows you to generate a hash for each possible key type on a map, right? A map can contain keys of booleans, of integers, or of strings. But if we have this method of hashing those types to the same hash every time, now we have the ability to key like into our map and find the value for it. Okay, I'm gonna pause there for questions for a second. Does that make sense so far? I know this part like kind of tripped me up at first, because like going from like why we're not doing it to like here's how we solve this was pretty quick. But does anyone like want me to re-explain this, or like have questions around this, or why we even need this in the first place? Hello, Max. I love seeing this. It's so nice. Cool. All right. So the idea now is that we're calculating like a little hash essentially for our given types. So now, regardless if we store like a literal 1 in the hash key, or like a variable that contains the value 1, no matter how we store it, 1 is always going to map hash back to 1, and we'll be able to do map comparison, which is nice. So that's cool. Awesome. With that, he said, once we have like that in place, now if we had that like name 1 and we put it in a map, and then we had name 2 that was a completely different like way of defining the name, and we put it in the map as well, you'll see that they do actually have a collision here, which is what we want, because now we can like go into the map and see if anything with that given key exists. Yeah, this was, I don't know, I felt like this was, maybe what tripped me up the most is like these examples kind of, I would have liked them to just like made a example test case rather than just like running code linearly. Whatever, it's fine. And then the author takes it a little bit one step further and says, not only can we create this little hash key that we're doing here, but we can extract that out into like its own type here. So you have like hash key, hash pair. And the reason why we're storing the pairs here is so that we can get like the underlying type and pretty print them a little bit better. So that's cool. Yeah, and that's that for this. Oh, and he ends this part saying, let's make it an interface so that way we can use it in our tests and whatnot. Cool. What else? This is the part where he evaluates the actual hash map. And honestly, there's not much here that's very interesting, with the exception of like, if we run into a hash literal, you have to evaluate the hash literal. And the act of evaluating it is very similar to walking the array like we did before. We just range over the pairs that we've got, get the key, hash the key, get the value, store it. So like this was pretty straightforward if you followed it linearly. What I do think was cool was where he actually like does the index expression. So like keying into a map and getting the value back out. I thought that was pretty cool. And I'm going to just skip to the code there because the code's pretty straightforward. Remember when we were like doing the same thing with arrays, supporting the index operation? Same thing happening here, but we're now doing it for hash maps. And we're basically saying like, hey, if the type on the left-hand side of our square bracket is a hash, then evaluate it as a hash. What does it mean to evaluate it as a hash? It means to check if we have a object hash type, get the key from it, get the pair from it, and return its value. So super straightforward. And congratulations, you literally have a fully fledged programming like language here at this point. I keep doing exit. And you can do things like this. Let people equal, and then we'll do a hash map. So Matthew will be, I don't know, like true or something. And we'll do like Omi is false because he's not here. And yeah, so now I have people. So if I print out people, you'll see the things. But if I actually index into this and get people, the key at Matthew, I will get true. And if I did the same thing with, they really need to support like up and down arrows. People at Omi, I will get false. And the author even makes a pretty cool example here that I'm just going to copy and paste out of the book. Boom. He does this. It's funny that he used people and I use people. I forgot that he did that. I just happened to do that. And he does this case and he says print out people. And notice how this is an array of hash maps. So there's like nested types, and it works because everything we've built so far works. I thought this was kind of magical. So you can do like people 0, which is the first hash map, and then like name, and you'll get Alice. Sorry, I meant to put that semicolon, but it's fine. So it was pretty cool. This is kind of nice to see because we went from like nothing and now we have like what we'd consider a programming language. I thought this was pretty cool to see. Like this is almost pretty much valid like Python at this point, right? Like this is kind of what Python's doing under the hood. Like this is what it looks like. So I thought this was pretty exciting. And then the author says he ends. I thought the way he ended the book was kind of nice. The author says, "Well, we did all this cool stuff. We have function part. We have lexing of source code into tokens. We have parsing of tokens into AST tree, and then we have evaluating the AST into like values and stuff, results. And we have functions, we have strings, we have booleans, we have integers, we have hash maps, arrays, we have all these cool things, conditionals, all of this stuff in this language. So we should be proud. But one thing we've never implemented was a simple print statement. So in all of the things that we've been doing, we have never ever implemented a print statement. The author chooses to use puts here. So it's like put standard out or whatever. They used to choose to call it puts. And if you run puts like, Matthew or something, you would just get Matthew printed to the screen. And the null that you're getting there is the value that was returned from puts, which is nothing. And then the author basically ends the book kind of with like a little mic drop. He was like, "Hey, we never had a print statement, so we could never do the basic thing of all, which is to." And he makes the print statement as a built-in, which is very simple. And he's like, "That's it. We have a print statement now, so we can do the best program of all, which is Hello World." And he literally just ends the book right there. I thought that was kind of cute because most like books start with like Hello World when you're learning programming, and this book kind of ends with Hello World. And I thought this was kind of, if you think about it, it makes sense because like this whole book was on building a programming language, right? Implementing a programming language. And now that we have done all this work to build and implement a programming language, we can now start using it. And where do you start? You start with Hello World. But we end with Hello World at the same time. So it was a little cool. Cool. And that's pretty much it. That's the book. I thought this book was really cool. I understand so much more about like how like lexers and parsers and whatnot are meant to work now after just reading this book and like looking at the Go code. I didn't like write all this from scratch. I kind of used the code that they gave me, but even just reading it and like talking about it with you all, I learned a lot. Any questions, comments, concerns anyone have before we call it?
I also like I haven't fully finished the book. I'm like halfway through 4, but I really enjoyed it as well. It was I think it was my first like programming book in general, so it was quite difficult to kind of keep up with it at times. But
Yeah.
just breaking down how something is turned into how a programming language works under the hood was been like super helpful, and it was awesome that you took the time to demonstrate this. I really appreciate it.
Yeah, of course. No, I enjoyed like learning about this stuff, and I never studied CS in college. So like I never learned about like programming language internals or these people that come out of college saying, "I built my own toy programming language." I'm like, "How? How the hell did you do that?" I don't know. So I thought it was pretty nice to finally take a step back and like read this stuff and see how it does under the hood. And I know this is not a production thing. This is just for learning. But now I know the concepts. I know what it means to lex. I know what it means to parse. I know what it means to evaluate. Like I know these things now. So I thought that was cool.
Yeah, exactly.
There was a GopherCon talk. Uh GopherCon talk Lexer or something like that. There was, I forget the person's name, but he had like an image GopherCon talk, like it was like from something to Hello World or something, and he showed like the steps Yeah, I was trying to look for the image because there was like an image there that had like this long little snake diagram of like all the steps the Go compiler took to make your source code like executable. Yeah, it was this talk. Jesus Espino, this one. It's this one right here. This is probably gonna like get me in trouble, right? Is YouTube gonna like be mad at me that I did this? Hold on.
Fair use.
Fair use. Fair use. Yeah, it was this image. So like I'm gonna make this big for a sec. And this kind of still is a little small. Make it big. But like he showed this talk and he said like file, lexer, parser, type checker, IR generator, all this shit. And he just went through this and these all the steps that happen. And I remember I was literally sitting in the audience for this talk and I was like, what the heck is lexing and parsing? I was literally so confused. I was like, what does this even mean? I just know file and execution. Like I don't what is this dude this dude's crazy. What is he talking about? But now like I get it. I see what they're talking about. Like, you are taking the source code and you're making tokens. I know what a token is now, right? All these terms on this screen look familiar now, with the exception of like the IR stuff, but it's fine. Mind you, Go is a compiler, so it does more than just an interpreter. But I understand like take file, read source code, lex it, get tokens out, parse it, get AST, and then technically like parse AST and execute, right? So like we can kind of skip down. But I don't know. I just remembered after I finished this book, I was like, I remember this so vividly. I didn't know what the heck this guy was talking about. And now I feel like I know so much more just by reading this book. But yeah. Cool. Oh, and I will say the author, where did I put it? Yeah. The author has like a lost chapter of the book where he like shows you how to do a macro system for Monkey, which I thought was pretty interesting. I didn't even know this existed until I saw this. So you can find it at interpreterbook/lost. And it's just like another chapter, going just one step further. And he defines macros. And if you're familiar with C or Rust, you'll know like what macros are. And I'm going to read this. I'm not going to do a book club on this one. I'm going to read this in my spare time because I am interested in how that like kind of works under the hood. And yeah, so they have this book. And then the next book that he has is writing a compiler in Go. It takes it even further. And instead of just stopping at an interpreter, we now build a compiler. So I'll be reading that book as well. But yeah, and that's it. Go back to the top of the page. Any last minute questions before we absolutely call it?
Nah, thanks for taking the time. I look forward to the next book club that you do. If you want to.
Yeah, I have so much like. Let me pull myself on big screen. I don't even remember which one it is. Is it? We'll see.
Cool.
But cool.
For somebody that has, not much experience with reading programming books, is there anything that you recommend? Anything that was like really, really good for you in the past that you've worked with?
Like ways to read it better, like to.
No, just like other material that you've read in the past that you would recommend.
Oh yeah. Let me look around. For like programming style stuff, just specifically.
Yeah.
Most of the things I have are like specific to technology.
Gotcha.
But I'll check over there and see like what I have that's like that I remember is like more general but good. But usually the stuff I read is more specific to something. I like the way the O'Reilly books tend to read personally. So if you are looking for like a recommendation on like styles of book, the O'Reilly books tend to be pretty good quality. I have actually never read a packed book, so I have no idea how those feel. So like there's that. But yeah, I can get you some stuff. Otherwise, I think it just comes with time, to be completely honest with you. Like I remember when I read my first programming book, like in college, because even though I didn't do CS, they made us take like a Java course, and they gave us a book for it, and I was like, this is horrible. Like I don't want this. So I think it kind of takes time too. You just read through it and get better out of time.
Yeah. But if you have any books that just come to mind that you read in the past that were like super impactful,
Yeah. I'm gonna take a look at my shelf back there and look at ones. The one that like I did like a lot was the Phoenix Project. I liked that a lot. Not because it was like a programming book, it was more of a novel rather than a technical book. But it just like opened my eyes to the like how technology is solving business problems and how it's like evolving to solve business problems better. But yeah, I'll take a look at the shelf I got back there and let you know, like which like and yeah, I'll look at them and be like, oh yeah, that book I remember, and then whatever ones that happens to me for, I'll send them to you. Cool. All right. Well,
thanks, Matthew.
Caleb, Max, thank you. You all are great for joining. Hope you had a good time in learning things, and I recorded these so that we can have them forever. So cool, man. All right. See you all in the next one. Bye.
See ya.